Real agents do not just fail. They fail halfway through a tool step. LangGraph lets you recover from that state without restarting the whole workflow. This is the pattern you'll be able to implement by the end, which safely resumes a failed agent state and retries the failed step until the run completes. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Agents call external tools. Those tools can time out or crash during a single action. The pain is not just the failure. It is rerunning the whole flow and duplicating side effects like payments, emails, or database writes. Success looks like continuing from the exact point of failure. You want retries that are safe. You want checkpoints that remember what already happened. LangGraph gives you a structured way to do that in Python without reinventing the persistence and routing logic. The intuitive idea is simple. Save the agent state as it moves between steps. When a step fails, mark the current status and loop back to retry only the failing step. Make the actual tool call idempotent, so retries do not create duplicate effects. Finally, allow resuming from a saved checkpoint identified by a thread ID, so a crash becomes an incident you can recover from. Strengths are correctness and lower cost from avoiding full reruns. Weaknesses or added complexity and some latency from retries and back off. We will build a tiny LangGraph that demonstrates those pieces in sequence. You will see a single node run once, then a node wrapped in a retry loop, then one that keeps side effects idempotent, then how to resume from a checkpoint, and finally, how to add exponential backoff. Each step is small and concrete, so you can lift the pattern into your own agent code. First, we build a tiny graph and execute a single step to show state checkpointing. This snippet builds a tiny LangGraph and executes one successful step. A state graph is created to manage state transitions, and memory saver is attached, so each node write is checkpointed. The function charge marks the operation as charged and increments attempts, returning a partial state update. The node is wired between start and end, then compile produces an executable app. Finally, invoke runs the graph with an initial state and a thread ID to identify the workflow instance. The charged flag comes from the function's return and is merged into the graph state. The print confirms the node ran, and the state was updated as expected. Next, we introduce a conditional retry loop, so a failing step can run multiple times. This example adds safe retries in LangGraph using conditional routing. The function charge increases the attempts counter and returns a status of retry until attempts exceed fail until. After that, it returns done and sets charged only once. The helper cond reads the status and drives add conditional edges, so retry loops back to the same node, while done advances to end. Memory saver keeps state at each step, so progress is preserved between retries. The input includes fail until, which controls how many times the node will retry. Increasing fail until increases attempts and total latency. Reducing it shortens the loop. The print shows total retries used and confirms the run finished. Now we make the tool step idempotent, so retries do not cause duplicate side effects. This code adds an idempotent tool step to LangGraph, so retries don't duplicate side effects. The function charge tracks attempts and signals when it is done. The function apply simulates a tool call that writes a transaction ID. It checks the charged flag, so it only writes once, even if re-entered. The cond function reads status, and add conditional edges routes retry back to charge and done to apply. Once apply runs, the charged flag and TXNID become part of the state, preventing duplicates on further loops. The compile and invoke steps execute the graph to completion. The printed transaction ID confirms one successful, deduplicated effect. Next, we simulate a crash and resume from a saved checkpoint, so a partial run does not get lost. This snippet resumes a LangGraph workflow from a saved checkpoint. The CFG variable sets a thread ID so memory saver can find the right state. The call to update state seeds the checkpoint to reflect a failed attempt and a retry status, simulating a crash or external interruption after a partial step. When invoke runs again with the same thread ID, the graph continues from the checkpoint, executes the next retry, and finishes. This approach enables incident-style recovery without redoing already successful actions. The printed resumed attempts and final status show the run picked up from attempt 1 and cleanly completed. Finally, we add a delay strategy so retries back off and avoid hammering downstream services. This example adds exponential backoff to LangGraph retries and times the run. The function charge increases attempts and, while still failing, sleeps for a short period that doubles each retry using time.sleep. The graph loops on retry and exits on done via add conditional edges. After compile, a timer around invoke captures total elapsed milliseconds to reveal the throttle's impact. Raising fail until increases the number of retries and total delay. Reducing it speeds completion. Increasing the base sleep raises latency but can protect downstream tools from overload. The printed elapsed MS and attempts values confirm backoff applied across the retry sequence. In a real project, this maps to things like payment retries, API calls with rate limits, or long-running data jobs. You checkpoint before any external write. You make writes idempotent by storing a transaction ID. You use a thread ID per workflow, so each user or job resumes independently. Recap. What it is: a pattern of stateful graph nodes with checkpointing, conditional routing, idempotent tool calls, and resumable thread IDs. When to use it: when a tool step can fail mid-action, and you must avoid duplicate side effects while resuming work. One caveat: it adds orchestration complexity and some retry latency that you must test. Next step: add timing and accuracy checks and scale the graph across many thread IDs to measure latency and correctness under load. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.